This is going to be a two-part lesson. Firstly, we are looking at heat capacity. So all objects naturally resist a change in heat. Some objects are obviously better than others at resisting this heat change. So as an example, it takes 4.184 joules, this is kind of a magic number, of energy to raise 1 gram of water by 1 degree Celsius. Again, it might be hard to picture that. We'll come to some examples that'll help put that into perspective. Okay, so talking about heat capacity. So objects that are good at resisting a change in heat are said to have a high heat capacity and will remain cool. It almost seems backwards for a second until you think about it. So there are a few objects that have high particular heat capacities, or high heat capacities, and so they will remain cool when a lot of heat is applied to them. The opposite, objects that are bad at resisting heat changes, they heat up quickly and they have low heat capacities. And like all of these things, you apply heat to them, they will seem rather hot. So an example here, on a hot sunny day, would you prefer to sit on a bench made of wood or a bench made of metal? And I need you to consider heat capacity in your answer. So thinking about this, if you think about the bench made of metal, it's got a low heat capacity, so it'll be really hot. That says hot. And the bench made of wood has a high heat capacity, so it'll seem rather cool. So that would be the obvious answer. So the bench made of wood, because it would resist the heat change. So that is heat capacity. Now we're going to look at specific heat capacity. We're adding one extra thing to our definition. It is represented by the letter C. So it's the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. Now it's got a rather wild unit here. It's measured in joules divided by grams multiplied by degrees Celsius. So it'll probably more typically look like that. Now here is a table. So I do have one, table 2 is provided somewhere on the website, or you can just simply Google these values. Now they should be, rather consistent. I mean, there's probably a slight variation depending on the source you're looking at. But there are some values. Now, again, just to put this into perspective, these two are rather close to each other, water and iron. And really what it's saying is that, water's value for specific heat is about 10 times bigger, right? It's about 10 times larger than its iron friend here. So that means it would resist a change in temperature like 10 times as well. So iron would heat up a lot faster than a sample of water. So we have an equation to help us calculate this. Q equals mc delta T. So to define all our variables, Q is energy that is measured in joules. M is mass that needs to be measured in grams. If you have something in kilograms, you need to convert. C is the specific heat capacity, the aforementioned one. And we have a delta T, which is equal to our second temperature minus our first temperature. I've never really been a big fan of that. I prefer more to think of it as our final temperature minus our initial temperature. The reason I like that is because you can't always depend on the question to give the values T1 and T2 in that order. Perhaps even in a lab, you might just make more sense for it to be T final and T initial. And of course, these are measured in degrees Celsius. Now, the kicker is they can be either positive or negative. So energy can be released to the surroundings or taken in from the surroundings, one or the other. So let's do a couple of examples before you get to work here. So let's determine the energy required to raise 100 grams of water by 10 degrees Celsius. So there are your 4 values. The question's asking us to determine the energy. It's given our 100 grams of water, because that's what's going to be undergoing the temperature change. So you need to look up the specific heat capacity of water at this time. You might remember it from an earlier slide as 4.184, and it does have a crazy unit, but let's leave that off. Now, with our change in temperature, this question's already given you the change in temperature. There's no 2 values, there's only 1, so it's already been done for you. So then it's just a matter of writing down the equation, filling in the values, and coming up with an answer. Now this is energy, and so it will be measured in joules. So that's about as simple as these questions get. Let's make them a little bit harder. So we have a 100 gram sample of water is sitting at 20 degrees Celsius. Determine the energy required to reduce the temperature of the water to 15. So we have a mass here, and we have two temperatures. So it's initially sitting here, so that's our T initial. Its final temperature is 15 degrees Celsius. So let's go ahead and plug in our numbers. We have a mass of 100. Again, our specific heat capacity water, 4.184. And now we're going to subtract our two temperatures. So once you get them in the right order, it's 15 minus 20, which actually gives you -5. I think that makes sense. The sample is cooling off, isn't it? So we'll write our equation, we'll plug our values in, and when we do that, we actually get a negative energy value. And just to be cool, we'll convert that to kilojoules, because that's going to come up in a little bit here. So there you go. So this example is just to show you that you can have negative values, and that is absolutely fine. A metallurgist is working with 10-gram samples of gold and silver. Determine which metal reaches the highest temperature when 100 joules of energy is applied to both samples. So there's our formula, but this question is asking us about a temperature change. So we actually have to rearrange your equation. So there's a couple of different ways you can rearrange this one. So for gold, we've got our equation. Now, we've got our 100 joules there. Here we have a 10-gram sample of the gold. Normally these are in water, but this one's just sitting out, pretend. And this value I had to Google, so I just Googled specific heat capacity for gold, and the answer came up. And when you do the computation, you get 76.92 degrees Celsius. Continuing for silver, same equation. The only thing that changes is my specific heat capacity, which I didn't seem to type in properly. There's 0.237. And when you do that computation, you get 42.2. So determine which metal reaches the highest temperature. That would be our gold. It gets the hottest because I guess it has the lowest specific heat capacity. So there are a few questions where you may have to get into some algebra because there's maybe they'll give you an initial temperature and asking for a final temperature, and there's also some questions in the homework where you're gonna have to figure out what metal it's talking about. So you're gonna have to calculate the heat capacity and then compare it to known values and see which metal you're talking about. So go get that done. We're going to be looking at a couple of things in this section. We're going to be looking at calorimetry, energy transfer, and molar enthalpy. We'll get to that in a little bit. Let's talk about what a calorimeter is. It's simply a device that is used to measure a heat change. So essentially it's just a well-insulated chamber like a thermos that can hold water, and that water is what's going to absorb the heat change. And there's also a thermometer there to measure the heat change. So there's a couple of examples here. This is your classic styrofoam or coffee cup calorimeter, and then these ones are that's a bomb calorimeter. Those are your big boys right there. So there are two types of calorimeters. I mean, there's only one type, but it's the assumptions that we use that set them apart. Firstly, we've got a simple calorimeter. So with this, we assume that the water is the device that absorbs all the heat of the reaction. We assume the calorimeter absorbs no heat, and we assume no heat is lost to the surroundings. Probably the coffee cup calorimeter you saw on the previous page is probably the closest thing we've got to a simple calorimeter, because the styrofoam is really not going to undergo a heat change. So if you think back to all the questions that you did in the first part of 5.2, those would have been considered in a simple calorimeter. The calorimeter wasn't undergoing heat change. So the complex calorimeter, we assume all parts of the device absorb heat. So if it's made of metal, the metal is going to warm up or cool down. And we assume all parts of the device have the same initial and final temperatures as the water. So we've got this equation that we became familiar with in the earlier section, but we actually need to do it twice because we have water that's undergoing a heat change and probably the device itself. So here's a question. A steel calorimeter with a mass of 322 grams is filled with 225 mils of water. Now we do want to work in grams, but hopefully you remember that 1 mil of water is equal to 1 gram. So technically it's 225 grams. The starting temperature of the device in the water is 10.6 degrees, and we have 1.02 grams of ethanol that gets burned, and our temperature rises dramatically. So we've definitely got an exothermic reaction. So firstly, let's calculate the heat change here. So I just went ahead and took the water numbers. There's our mass of the water, our specific heat capacity of water, and our temperature change. And then I repeated with the mass of the device. the specific heat capacity. So it said it was steel, so a quick little Google search yielded that value. And then the same temperature change. Remember we said the temp change will be the same for the water and the device. Plug your values in, and you get about 30,000 joules or 30.11 kilojoules. Now we have to be careful here because this is an exothermic reaction. And what we've learned, or are currently learning, is that anytime we have an exothermic reaction, our answer is in fact negative. Exothermic reactions have negative values. And this is the case where we just have to rationalize this one. Our answer came out to be positive, but really our system has lost the energy, the surroundings is warmed up, and really we have to focus on the system. So we end up with a negative value there.